Hello and welcome to this section of the Physics 3 tutor. This section we're going to continue to talk about magnetic fields, magnetic forces. We're going to work a couple of problems to really give you a little bit of practice. Now if you remember, in the last couple of sections we were talking about the magnetic field. A lot of it was just getting you comfortable with what it is. There was really only one equation in the entire section, and that was the force that a magnetic field exerts on a particle that's moving through the field, because it has to be moving, right, in order to get a force at all. So these problems are going to zero in and focus on learning how to use that. And the first problem goes like this. An electron in a TV tube moves at a speed of 7.2 times 10 to the 6th meters per second in a magnetic field of 83 milliteslas. At some point, the acceleration of the electron is 4.9 times 10 to the 14 meters per second squared. What is the angle between the magnetic field B and the velocity V? So there's a lot of information here, but we know how to do this because when you look at it, first of all, we know it's an electron, so we know what the charge is, right? We know what the magnetic field strength is, 83 milliteslas. We don't have any information about the direction of the field. We don't have any vectors that are governing the direction of the field. We have the velocity, but again, we don't have a direction. We don't really know a direction, and we don't have a vector for either one of those quantities. We know the acceleration. We're going to figure out how to work that in later, and we're trying to find the angle. So if you think back to the actual equation, the original equation that we talked about, the full version, it's QV cross B, right? Really, we know what the charge is. We know what the velocity is, and we know what the magnetic field is. We don't know the directions, though, so we can't really compute a true cross product. So this is a great example to try to use sort of the simplified version. The magnitude of this force, magnitude, right, is going to be QVB times the sine of the angle between them. QVB times the sine of the angle between them. Because ultimately we're trying to find out what the angle is between them. That's what we want to know. We don't care about the direction everything's pointed. All it's asking for is the angle between them. So if we could somehow put everything into this equation and calculate the angle between them, because we can find what the sine is, the inverse sine, then we'll have the answer. The problem is, the problem doesn't actually tell us what the force of this magnetic field is exerting on there. We don't know that. So let's see what we do know. We think we're going to use this. What do we actually know? Let's write that down, because it's very helpful to do that. The velocity is 7.2 times 10 to the 6th meters per second. The magnetic field strength is 83 milliteslas. Okay, that's good. The acceleration, we're not sure how we're going to use that yet, but we know that it's 4.9 times 10 to the 14 meters per second squared. But we don't actually know the forces, so we can't just plug into this formula and get the answer. My advice is write down what you know. Obviously you know some stuff, so just write down what you know and you'll get partial credit for it anyway. So we're going to use the magnetic force magnitude, QVB, times the sine of the angle between these two guys. We don't know what FB is, so we're just going to leave it like this. We know what the charge is. This is an electron, right? An electron, you can look that up. It's going to be, it's really negative 1.6 times 10 to the minus 19. But for the sake now, let's just keep it as an absolute value. Let's say it's 1.6 times 10 to the minus 19. Now we know that this charge really is negative, so you might think, well, why don't you put a negative sign in front? Well, in this equation, when we use this version, we only care about the magnitude, the strength of it. We don't care about what direction it's pointing, right? So we don't really need to keep track of signs for everything, because that's the whole point. We're not keeping track of the direction of these either, right? So what is the magnitude of the velocity? We know what it is. That's 7.2 times 10 to the 6th. And what is the strength of the magnetic field? It's 83 milliteslas. Never work in milliteslas. Always convert it to teslas. So we're going to change that milli into a 10 to the minus 3. And obviously, it's the sine of phi at the end. So we don't really know much, but we know that the magnetic force is equal to all these things multiplied together times whatever the sine of the angle is between them. So we can do that multiplication, just to simplify things a little bit. FB, when we take this times this times this, what you will get is 9.56 times 10 to the minus 14. We wrap that in parentheses to make it easy to read, times the sine of phi. Okay, so we've made some progress, but we cannot find the sine phi because we don't know what this is. So obviously we can't just get the answer straight away. We have to use some more information. And look, they've actually given us some other information. It tells us at some point the acceleration of this electron is 4.9 times 10 to the 14 meters per second squared. So we know what the force is on this particle. We don't know the answer in terms of a number, but we know what the force is equal to. We know the acceleration. Anytime you think force and acceleration, you should think Newton's law, F equals ma. So that's something you can always use, right, to get the answer that you seek. So what we're going to use is F is equal to ma. The force acting on this particle is equal to what we have here. So it's 9.56 times 10 to the minus 14 times the sine of phi is equal to m. What particle are we talking about? In this case, it's an electron, so we need to know the mass of an electron. Of course, that's a constant. We know that. That's 9.11 times 10 to the minus 31. That's in kilograms, so we always want to work in kilograms. And the acceleration a is given to us 4.9 times 10 to the 14. Now we're making progress. Because we've used Newton's law, we have got everything here with a number except for this. So the sine of this angle is equal to, if you take these two numbers and multiply together, and then you divide by this guy, what you're going to get is 4.66 times 10 to the minus 3. And then if you take the inverse sine, what you'll get, in degrees anyway, is 0.267 degrees. That's the answer. So less than 1 degree, right? So this is top to bottom, a pretty easy problem to actually work out. No calculus, nothing too hard, but the logic is really what's difficult in all physics problems. They're all easy once you know how to do them, right? So practice them, make sure you understand how to do it. Basically, we know we're going to use the force equation because we have a particle moving in a magnetic field, so that's a given, right? We don't really even know the directions in terms of vectors of these fields, so it's a huge clue that we're not going to use the full-blown cross product. We're going to use the magnitude. All we care about is finding the angle. So if we can plug in everything else, we're good. So we do that using everything we know, and we realize we can't find the answer because we don't know what this is. But then we start thinking, how can we find that? We know F equals ma. So we put F over here on the left-hand side equals the mass times the acceleration. We solve for the sine of the angle, and we do the inverse here. I did it in degrees. You might want to do it in radians, but in terms of me visualizing what's happening, degrees for me was easier here. So that's a huge clue. Whenever you don't actually have the information given to you, obviously you're not going to be able to do a cross product. All right, the next problem is an electron has a velocity, and the velocity is given as a vector. It's 2 times 10 to the 6 in the I direction, which is the x direction, plus 3 times 10 to the 6 in the j direction, that's meters per second. It moves through a magnetic field that has a strength. The magnetic field strength is 0.03 in the I direction, minus 0.15 in the j direction, that's in Tesla. The question is, what is the force on the electron? Magnitude and direction. This really is almost a cookie cutter straight in problem because you're given you know it's an electron, so you know the charge. You're given its velocity, you're given its magnetic field. You're trying to find out what is the magnitude and the direction that this field exerts on this force. So that's a no-brainer. You're given the vectors, you're going to have to do the full-blown cross product. So FB, the force from the magnetic field, is QV cross B. And just to make it clear, what is given is the velocity is, as a vector, is 2 times 10 to the 6 in the I direction, plus 3 times 10 to the 6 in the j direction. That's in meters per second. Don't get too scared off by this. What this is really saying is this particle is moving at this speed in the x direction plus this speed in the y direction. That's all it's saying. Magnetic field is given to us in the problem as 0.03 in the I direction minus 0.15 in the j direction, and that's in Tesla. Again, don't get spooked. All it means is the field strength is 0.03 Tesla in the x direction, basically, and it's negative 0.15 Tesla in the y direction. So both V and B have components pointing in x and y. right? And we're trying to find out what the final force is. There's no way you're going to be able to do this without doing the full-blown cross product. So that's what we're going to do. But to make it easy on yourself, even though the final answer is going to be Q times V cross B, just work on getting the cross product first, and then we'll multiply later. So let's find V cross B. Now, most of you guys have calculators. Maybe you can use them on a test, maybe you can't. You could type this in as a vector into a calculator. You could type this in as vector into a calculator. You could cross them and it would spit out a vector. That's fine. If you want to use your calculator to compute the cross product of those vectors, that's fine. You're going to get the answer, bam. But most professors are not going to stand for an answer like that. They're not going to just say, hey, write the guys down and give me the answer. They're going to want you to show some work. So I'm going to show you how to calculate this manually. I'm going to show you how to calculate this cross product manually by hand so that you'll have that tool when you get on your exams. And once you get the hang of it, it's really not that hard anyway. The way to do it, there's lots of ways books teach you how to do this. I have a way that I've always used and I've never forgotten once I learned it. It may look crazy at first, but it is easy to remember once you get the hang of it. V cross B. This is how I write it. Basically, what you need to do is write it as the determinant of the following matrix. On top, you need to write, because this is 3 dimensions, you need to write I, J, and K. Like this. Let me go ahead and draw another matrix bar like this. And what we need to do is, since we're crossing V into B, the first vector we put is V. So the X component is 2 times 10 to the 6. The Y component was 3 times 10 to the 6. The Z component was 0. There was no Z component. So you put a 0 there. B, the X component was 0.03. The Y component was negative 0.15. Z component was 0. So really what it boils down to is you taking the determinant of a 3 by 3 matrix, right? You have an X component of both of your vectors, a Y component of both of your vectors, a J or a K component, however you want to call it, of both of the vectors. So again, you could put this determinant in your calculator and get the answer as well, but my goal is to teach you how to do everything by hand so that you know. It turns out taking a determinant, everybody watching this should know how to take the determinant of a 2 by 2 matrix. You just multiply as in an X pattern and add together, and I'll show you as we go here. A 3 by 3 matrix is a little more involved, but once I show you the trick, it's not that hard. What you do, all right, is the answer. First, you write the answer of the I component. First, you write the answer of the I component. So what we're going to do is I'm going to put a bracket here, the I component. You mentally cross a vertical, just kind of like put your hand over here, because we're talking about the I component. Now we take the determinant of what's left over here. So here we have 3 times, I'm going to write everything out just to be clear, 3 times 10 to the 6 times 0 minus 0 times this, negative 0.15. So again, the answer to this determinant, the I component, the X component, you cover this up and you take the determinant of what's left over. And it's a 2 by 2, so it's this multiplied together minus this multiplied together. That's all I've done here. Of course, this is all going to be 0, but I'm writing it all out so you can see. When you get to the J component, you have to remember to put a negative sign out in front. And then you cover up the J column and you take the determinant of what's left over. Now forget this is here. So it's this times this, 2 times 10 to the 6 times 0 minus 0 times 0.03. Again, cross it out. It's this times this minus this times this. You have to remember to put a negative sign. That's just the way it's derived. Plus a K direction. Here, you mentally cover up K, and this is the only non-zero terms we have. We take the determinant of what's left over. We'll have 2 times 10 to the 6 times this, negative 0.15, minus this, 3 times 10 to the 6, times this, 0.03. All right, so what we should be able to see is, since this is times 0 and this is times 0, this entire thing basically goes to 0. Since this is times 0 and this is times 0, this entire thing goes to 0. So there is no I component and there is no J component of the answer. So what we're going to have is V cross B. We have not computed the answer. This is just V cross B. It's going to be equal to when you do this math here, the k component of it, if you multiply this times this minus this times this and just do that and get the answer, what you're going to get is negative 3.9 times 10 to the 5. That's the k direction. Now stop for a second and realize what you've done. You've taken the cross product here, right? You've done v cross b. You could have done all this in the calculator. We're just doing it by hand. The whole determinant of the matrix thing, that is just a means to calculate v cross b. I really encourage you to learn it. I've taught it in my calculus classes. I've taught it in my other physics classes. It really pops up a lot. If you need to calculate a cross product quickly, do ijk, component, 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 take the determinant, learn what I'm teaching you here, and you're going to get the answer every time. Now, the actual force FB is not V cross B, it's Q times V cross B, which means Q in this case is an electron. That's what we're starting out first. And so an electron, since we're using the full version, we're going to use the sign, negative 1.6 times 10 to the negative 19. That's how many coulombs we have, times this guy, negative 3.9 times 10 to the 5. Of course, it's in the k direction. So basically, we take the result of the cross product and we just multiply by the charge, which is sitting out in front. So when you do this multiplication, you have the cross product here multiplied by the charge that we're actually dealing with. And then the force is going to be equal. Negative times negative gives me positive 6.24 times 10 to the minus 14, acting in the k direction. Acting in the k direction. All right, so before we go any farther, let's make sure this makes sense, right? Up here, we know the velocity of this particle lies purely in the xy plane. We know that the magnetic field also lies purely in the xy plane. We have found that the force acting on the particle is not in the xy plane, it's coming straight out of the plane in the z direction. And that makes perfect sense, because pretend this is the xy plane, right, like this. If my velocity is somewhere in this plane, who cares what direction? I mean, these directions are really hard to visualize. It's some direction here. Magnetic field's also in this plane somewhere. When you cross them, the result pops straight out of the plane, which is exactly what we got. So that's a sanity check to make sure you're doing the right thing. Secondly, is to kind of just think about it for a minute. If this particle is moving along and the force is pushing out of the plane, it's going to tend to curve it, right? Change its direction. It's not going to push him in the direction of motion. He's pushing him completely perpendicular, trying to change his course, change his direction. And that's what the magnetic field always really does, right? And that's what we talked about in the beginning. Now, the second part of the problem says, repeat the same exact calculation, but do it for a proton instead of an electron. So don't sweat too much. Just look at this and say, well, the velocity has not changed. It's just a different particle, but the speed and the direction hasn't changed. The magnetic field has not changed. So because those are the same, the cross product is really all the same. So V cross B comes out to this. That's not going to change. What is going to change is that when you calculate the final force, it's going to be QV cross B. This charge is now a different sign, so that's going to change the answer. So FB, since we're now dealing with a proton, instead of a negative guy we had for an electron here, we're going to have a positive 1.6 times 10 to the minus 19 coulombs. It's positive because it's a proton. And we're going to multiply by negative 3.9 times 10 to the 5 in the k direction. This was V cross B. But basically, we keep this, and we just change the sign of this. So I think it's not a huge surprise what we're going to see. FB is going to be equal to 6.24 times 10. It's going to be actually negative. Negative times positive gives me a negative. 6.24 times 10 to the minus 14 in the k direction. And of course, what am I talking about? Let me go ahead and just make this. This is newtons, obviously, and it's in the k direction. And if we come down here, this is newtons as well, right? Newtons. And this is for an electron. So what have we found to conclude, right? So the electron is basically going to be pushed in the positive x direction because this is positive. The proton, because that's this problem, is going to be pushed in the negative k direction. So the magnitude is the same, the direction, because of this negative sign, basically means you're going in the opposite direction along z, so it's going down. So if you have this arrangement, like in the magnetic field here, and you shoot an electron into this guy, then what's going to happen in that case, the electrons want to curve up because the force is pushing them up. If you shoot a proton in, it's going to want to curve down. That's typically what you're going to see in all of these problems, is that whenever you do something with an electron and proton, because of the different signs, you're going to want to curve different directions because the force is going to push two different ways. Well, that wraps it up for this section. I wanted to give a couple of practical problems to show you how to use this equation, right? Which is, you know, a little bit involved, but really not that bad. In the first problem, we didn't really have to do a full cross product because ultimately it didn't matter in the final answer. We only cared about the angle. This problem, we wanted the magnitude in the direction of the force, so we had to do the cross product. Most of the work came down to calculating this cross product. You can do this with any method you want. You can go look in books and figure out how to take cross products, and there's different ways to do it. I like this because I can remember it. If you look in books and they say, here's the cross product, and there's a bunch of multiplication everywhere, it's going to be difficult to remember. It's easy for me to remember this because I just put ijk, xyz for the first term, xyz for the second term, and then I just go term by term. In the x direction, I do this determinant. In the y direction, I do this determinant, remembering to put a negative sign out front. Z direction, I do this determinant. Bam, 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 that's the cross product. The only thing you really have to remember is for the j component, you have to put a negative out in front. That just comes from the way it's derived, if you were to go back and look at how this method is derived. But that wraps it up. This is Jason with MathTutorDVD.com. Work these guys, make sure you understand them. Go watch the previous couple of sections where we talked about conceptually what the magnetic field is. Make sure you understand the difference between that and the electric field. I guarantee you'll be asked these sorts of questions on your test. And as we go forward, we'll learn about more applications of the magnetic field. We'll learn a lot more about how charged particles move through the field and some practical examples of when that's useful. And then we'll get into more theorems and applications later on throughout the course.